You have a bunch of animation data that are unstructured data, and you want to be able to use those to generate a new animation specifically along a path or something like that. Hi, I'm Jerome, and today we'll be looking at one of my favorite papers of all time, Motion Graphs, a paper from 2002. What I will do is that I will import my libraries as usual, and then I will import my character, and I will load one animation. And then we could see that animation to show you what it is. It's basically a character walking along and doing a bunch of stuff inside of that animation. But that animation is 7,000 frame long, which is a bit big for this kind of paper that was written a long time ago that was probably not dealing with that much of data. And to speed up a little the process, I would actually reduce that animation, and I will do it as if it was small clips instead of having one big animation. So what I do is that I only keep a few ranges. So what I would do is that I will only keep 3 pieces of the animation, and I will reuse that as being my animation. So I would just convert the animation itself. And now it's basically the same. I have the beginning of the animation, and then it would do a few walk and then jump in a different spot here. So that's one clip, then next clip, and then does the same here, a bunch of walking, and then it will walk, then jump. So it's basically 3 different clips, but I'm still packing them inside of one animation, which will make my life easier inside of the notebook. The paper itself would actually work with several clips or one big animations. It's up to you on how you want to do it. Then motion graphs. Basically, the idea of motion graphs is to have your animations and then build a graph out of it. And to build that graph, there will be a few steps to go through before being able to reach the graph status. And basically, if you go through the motion graph constructions, the first thing is to find the best candidate to make a graph out of it. So imagine you have 2 animations, and you want to figure out from which frame inside of a first animation you could reach another frame, and that would give you a transition that is smooth and doesn't pop. And so basically what you have to do is figure out inside of all your frames of animation, find the one that are matching so you could do the transitions. And there is several ways to detect those candidates. You could do it by checking the orientations of the bones and all that kind of stuff. But then, quaternions can be tricky. Finding just the saying that rotations on a small rotation on the hips can have a big impact, while a small rotation on the hands has nearly no impact. So what they've decided to do is that instead of looking at orientations itself, they said that what we see is actually a mesh. So what is the best solution to match is to make sure that visually the mesh will be matching. So you cannot test mesh with mesh because there will be a lot of vertices and that kind of stuff. So what they will do is that they will build a point cloud. And a point cloud is a lighter version of the mesh itself. So what I would do is that I would generate my point cloud with the same kind of idea. So basically I have a bunch of points attached to each bone. So you see for the hips, I have 5 points here that are attached. For the right up leg, I have 4 bones, right leg, 4 bones, and 4 points, sorry. So you get all those points. And to make my life easier at the end, also, instead of remembering those cloud points and then recomputing their positions every time, I will actually generate a point cloud animation. So that's what I did here. I get a cloud animation so that I get all my frames, all the points count, and XYZ. So I have a bunch of points floating in space. And so that's my animation now. And we could see what we have here is exactly this. we have the character walking, and then we get all the points that represent the point clouds attached to it as separate animations, but synchronized. So I have the point clouds. I can start to, I know how to build the point clouds. I can start to look at the paper on how they compute the stuff. So those point clouds will be used to actually compute the distance between two frames. So you want to calculate the distance between frame AI and BJ. And instead of considering just the point clouds of frame AI and BJ, what they would do is that they know that we want to do a transition between AI and BJ. So we would take a window of frames to do the point cloud. So the point cloud itself will not be frame AI, it will be frame AI up to frame AI plus 10, something like that. And frame BJ will be BJ minus 10 up to BJ. So what allows us to do is to make sure that not only the position will be the same, but then the velocities of those points will be the same, because they will be at the same position along several frames. So I'm not matching only one position, I'm matching the position, the velocities, and even the accelerations if the windows is big enough. And so that's what we can do here. See, instead of having one, I go a bit further here. Instead of having one point cloud, I can actually have all the frame in front. So that basically be, if I try to match frame A, that's frame A. And I want to match frame B, that's frame B. It's all the point clouds in the back that represent one point cloud in front, and one point cloud in front, one point cloud in back. So that's what we'll be comparing together to compute the distance. So my transition will be smooth. Now, to compute the distance between those two point clouds, we have to remember that they are in wall space. So my character is moving along inside of the animation. And we want to make sure that when we compute the distance, we compute the best distance possible if we did realign both characters together. And so instead of just computing the distance itself, what you do is actually you compute the minimized distance. So instead of computing just the distance, you compute the distance of pi. So pi is 1 point inside of my first point cloud, and p prime I is that corresponding point inside of the second point cloud, except that you could transform. So that's what the T is. It's a transformation of the second point cloud, and you could rotate theta and move x and z. So basically meaning that if I have one point cloud and I have a second point cloud, I can, with here for instance, I can rotate it and I can move it on the same spot. And then I'm trying to find the best stuff that gives me the minimal error possible, and that gives me the best alignment and the minimal error. Luckily, we don't have to actually run that minimized function because there is a closed form solution to that transform issues. And that's the formula for the closed form solution. So that's the angle and x and z offsets. And basically what I would do is have that functions as is. So it's really, see, the sum of the weights divided by the sum and all that kind of stuff. Give me the angle x and z, and I can return angle x and z. And we could use now that point cloud alignment inside of our animations directly to see what they do. And so what I have is, for instance, I would move these characters. So I get character in the back is my A frame, let's say. Character in front is my B frame. You could see that I'm computing the cloud alignments every single time. So of course, this guy now always stays more or less where the other guy is. And you get the error, the amount of errors that each point cloud is giving me. So even when the error is really big, the alignment is not too bad. And then I get the T that's allowing me to display what a transition would be if I was trying to do a transition between that frame A and that frame B. With a really big error like this, you could see that the transition is quite ugly. Basically, you could see that the feet are just sliding. It makes no sense at all. So I'm just basically sliding. And if I find an animation that has a frame that has a smaller error somewhere, can I find something? I'm 3000, I'm not too bad. Let's say 3000 here. And I try to do that transitions. Now I get transition that actually make a step. And so that transitions is more natural than the other one. So at least we can compute the alignments, we can compute the distance, and then we could see that the transitions, if we were to take a transition at that time, it would work. So that's give us the distance functions. And now what we need to do is to make sure that we can actually select when we want to do that transitions. So, and to do this, what we will do is that we will compute, basically this, we will compute the distance between every frame with every frames, and it will give us the error for every possible frames. And what I would do for this is actually, I would, instead of running my function that I wrote here, which is in NumPy, I will actually run that functions, rewrite that functions using the warp library. And the warp library is an NVIDIA library that allows you to write Python code that is compiled into CUDA and runs on your GPU. Because my animations is 1000 frames, so I actually have to do 1000 multiplied by 1000 tests. That's a lot of different tests. That's a lot of alignments and all that kind of stuff. So I will run that on the GPU. That will be faster. So I will compile this. So it's the same functions, basically exactly the same code, written a bit differently to run on the GPU. Now compute the alignments, and then the functions that compute the distance basically aligns the 2 point clouds, stores the angle X and Z values, so I will be able to reuse it. And then I compute the distance and I store the distance. And now I can run this here. So it takes a bit of time because it compiles the CUDA code, and I will launch that on my GPU and runs for every points inside of the system. And I will come back to you when it's done. Now it has computed all the distance functions, and then you could see basically that mapping between every frames with every frames. Of course, the line right in the middle there is the absolute best. It's a 0 error because it's basically said I want to do a transition with the animations that it should be playing anyway, because it's basically frame 200 with frame 200 is the same frame you're mapping. But then all the other one, all the different blacks area are potential transition you could take between different animations. So I should be able to take a transition from frame 225 with the frame 50. That's the kind of stuff this map shows us. And the white area is actually the 3 different animations I have. You know, it was 3 clips back to back. So that white area is actually transitioning from one clip to another. It's something, it's out of bound. You shouldn't be playing any animations right there in the middle. But that's give us an idea of all the errors. And then basically it's not enough to know that all those are really good candidates. We don't want to basically have a graph that says I can take a transition from this frame, this frame, this frame, this frame, this frame, and having a really big graph that goes nuts with tons of connections. What we want to do is what they did here. Well, their mapping is different. White is the best, black is the worst, and for me is the difference. But then what you try to do is to find the local minima. So the green dot represents the place where along all the frames around here, I'm the one that has the lowest error. So you should pick me and nothing next to me, because if I'm the best case, I will be the best case around me. So it's finding the local minima. And then I would do the same. I will compute the local minima. And again, I will do it inside of a CUDA kernel, just checking if for every frames, is all the frames around me worse and better than me? If they're all worse than me, I'm a good candidate, except if my error is too big anyway, or if I'm on that diagonal area, I don't want to be able to do transitions between myself. So I run it on the GPU, and now I have the same thing, except that if we go and zoom a little, you could see all those yellow dots basically means they are local minima that are good enough to take a transition. So all of those would be transition points now inside of my graph. And to build the graph, what I would do is having a node inside of the graph, which has a node ID. It knows the start frame in which the node starts, its end frames when it stops, and all the edges it can take at the end. So when you reach the end, that's all the possible edge I can take, all the transitions I can take. And an edge basically has a start frame, end frame. Does it blend or not? We'll come soon to it. An angle and X and Z, which were all the point clouds were aligned when we did that transitions. And basically, when I'm starting this, what I do is that I start with a list of nodes, list of edges, and the frame mappings allow me to know basically which frame belongs to which node. So at least I have something that maps the length of the animations. I can say, hey, frame 25 in my animations, which node do you belong to? And that kind of stuff. So that's what the frame mapping allows me to do. And I'm building the graph starting with 3 nodes, which are the 3 different clips, and without any edge between them. It's just 3 nodes, and that's it. And then to build the graph, you take every local minima you've found inside of the animation. And the way I'm doing it is, you can represent your graph several ways. The choice I made is to say that a node always play its entire animations up to the end, and only at the end can it take an edge to reach another node. I don't have edges that start in the middle of nodes and that kind of stuff. It's just at the end of the node, you need to take an edge. So if a local minima says, I'm leaving that node right in the middle of the node, the first thing I do is, here, I'm actually splitting the node in two different nodes. And I have the first node that points towards the second one, saying that is a transition without any blend, because basically it's just back-to-back animations. And there is the second edges from that goes from the end of the first node up to the actual frames I want to go in, with the blending informations and angle and transforms and all kind of stuff. And then you get all the edges and that kind of stuff. And then building the graph, you get this graph here. And then you could see nodes. So that's the entire graph, all the nodes I have here with all their edges and all kind of stuff. So lots of nodes that were building the graph. Now the issue we have when you do this, when build a graph like this one, what happened at some point is that you have this kind of graph. And for instance, if you're trying to traverse this graph to build animation and all of those, if you reach the node number 5, you will be stuck. There is no ways to get back inside of the animation. And so the node 5 is a no-go. It has to be removed basically from the graph. Otherwise, you might get stuck inside of your graph. And the way they're pruning the graph basically is to compute the strongly connected components, and you take the biggest one, the largest one, and that becomes the subgraph you keep. So in this case, the biggest strongly connected graph is just this 1, 2, 3, 6, 7, 8. Everything else is discarded because is not part of the biggest strongly graph. This one would be another strongly connected graph, but it's smaller than the other one. So keep on that, remove everything else. And that's how they prune the graph. It's a bit more complex because they also support the fact that you might have different type of animations inside of your graph. You might have, all locomotions and then all crouching locomotions and all kind of stuff. So what you would do is that you will compute a strongly connected graph per type inside of those, and you will keep the strongly connected, each of the strongly connected one for each style. In my case, I only have one, so it will be easier. I can only compute the main one, and that will be enough. And to prune that graph, to compute the strongly connected one, they use the Targent algorithm, which is what I've done here. It's a pure implementation of the Targent algorithm. I would not spend time explaining this one in this video. I might do another video talking about algorithms and covering this more in depth, but you can find a bunch of videos on internet anyway. Basically it gives me, that's all the strongly connected graph. It's well connected in our case here. So basically this one is the big graph I can use, and all of those are graphs that are just representing one node that they were completely out of access. So basically we want to keep all those nodes, and then we can discard all those. And I will do it as the paper is doing it. So you basically traverse every edges, and if an edge reach outside of the biggest subgraph, you delete that edge. Once you've done that for all the edges, you go through all the nodes that basically have no edges that leave them, and then delete all those nodes. And then what I'm doing is I'm remapping all the nodes, basically saying that, the node 3 and 0 were gone. I didn't like having IDs, dangling IDs. So basically remapping all my IDs now to go back again from 0 up to 500 something. That's just the remapping does. So what you have is that the number of edges I had before, so I deleted 50 edges and I've deleted 4 nodes. That's it. And once you have your graph like this, you could actually try to start to extract motion. So you could do a walk through your graph and generate, what I have here, the transitions here. The transitions itself, so you could walk through the animations and through the graphs and append animations back to back and make the transitions between different animations. And that's what these functions allow me to do. Basically, I have the append no blend. So, I've split a node in two. So I might want to actually be able to play back those nodes back to back inside of my animation again. So that's what the append no blend does. It takes the frame inside of my source animations, the frame I'm starting, the frame I'm ending, and the generated animations. So the generated animation is the buffer in which I'm building the animation I'm outputting. And basically the only thing it does is, imagine my character was walking and doing this, and then I said that I want to append an animation that is from here. It takes that animations, realign it back at the end of my animation and stick it there, and then keep going. So that's what it does. It realigns the clip and then append the animations to at the end of the generated animations and returns a bunch of animations it had added. And then you get the append blend, which is the one that actually do a real transitions between two frames. A bit more complex because it has to know the current frame I was playing at the end of my nodes, and where I'm starting my transitions and where I'm ending the clip I'm adding. And why do I need to do this? Is because, remember, I've said that I split nodes in two as soon as I had the transition, which means now that if my character is here, the first thing I need to do is to stick back the next few frame after, so I can do the transition, and then I can bring the new animation, put it in the same spot, and so the transition would happen. So it's a bit complex, so that's what I do here. The first thing is, if I was at frame 50, I take frame 51 to frame 60, for instance, and bring it back here, realign it. Then I take animation B. So if my animation A is here, my animation B, it was there. I take my animation B and I make it do the same offset that this one did. So my A moved here, so my B moved there at the same time. Do that with the B. And now that I have actually moved everything together, I can use the phi, X, and Z that was computed by the cloud alignments to realign this on the same spot. So bring A in the same spot, bring B relative and B on the right spot thanks to the cloud alignments, and then do the actual blend transitions. So blend a few frames, and when you did that, you get the blend, and then after happens the end of the animations without the blend. And what I do in the blend is that I compute this not as a linear blending. I do it with ease in, ease out, which is what they explained here, except that the mathematics are a bit weird, and I don't know why they go parameterize between -1 and k instead of 0 and 1. But basically what I do is that I will be using this one, which is the same formula that the one we've seen inside of the footscape cleanup. It's a ease in, ease out functions that allow me to get a value that goes between 0 and 1 linearly and give me a 0 and 1 with a ease in, ease out, which is that -2x cubed plus 3x squared, and that's the one I'm using here. So I do ease in, ease out blending, and then I get the app and edge, which makes my life easier. Take an edge, find the length of every node it has to do, make sure that it's a blend or not a blend, call the right stuff, and append that toward the animation. So as soon as we have this, I can do, for instance, a completely random walk inside of the animation, which is what I do here. I have a max frame of 1000, and you see, as long as I haven't reached at least 900 frames, I'm just adding randomly an edge to the animation, and that's it. And we could see what happens if you do this. You basically have this character that walks and do random stuff between different animations. What we see, all the different colors, is when which node is in, what the frame is playing, and the red and blue are the skeleton from and to transitions and the transition itself. And see, it goes and randomly pick any animation. But it's fairly smooth because we basically forced it to find smooth transitions between the two. And that's the extract motion I want a bit further. So searching for motions, because we haven't searched, we did actually walk randomly. And they say it's useless to walk randomly inside of a graph. I agree, it's probably a bit useless. Might be useful if you try to train neural network, but in most of the case, it's useless to do random walk. What you want to do is to be able to actually do a proper search through that graph. You do need to be able to give a purpose, a goal, and a cost function, say how quickly you're getting to that goal and how fast you get to that goal. And so the way they've decided to do it is, there's the naive solutions, as they said, is to go depth first search and search every possible graph walk you could do and pick the best one. Unfortunately, that graph is fairly big, and so as soon as you try to do this, you will probably kill your computer trying to find the best solutions, or wait for several thousand years. So there is a lot of different algorithms that have been studied along the years to solve these kind of issues. And the one they've picked in this case is to just do a branch and bound algorithm. Again, I will not go too much in detail with the branch and bound because I will probably do another video about it. But basically what the branch and bound does is just to make sure that when you start a search, every single time you want to keep going further into your search, you're checking if you haven't found a path that was better than that one before. So basically you keep track of the best path you found, and if you find something that is better than the one we had, you store that one, and as soon as inside of your search you detect that it will be worth, you stop. And so the way they're doing it here is that every time you happen an edge to your path, you compute the error, and that becomes the error, the amount of error or the cost of that path, and then you compare that every time with the best path you found, and you stop as soon as you add an edge that would say, but if I'm adding this edge now, it will be worse than everything you found. You stop the entire branch search. So that's what the algorithm here is doing. So I get the path, I get the last node, the amount of error, the number of frames that this path is covering, and then the list of edges. I don't need anything else to be able to rebuild an animation than the list of edges, because an edge will give me a node. I need to play up to the end of that node and then take that and the next edge and so on. So having the list of edges is enough for me to compute a path. And then the search algorithm is just, as I said, the branch and bound algorithm. And one stuff I could compute with the branch and bound here is basically saying, okay, I have a stop function. Say if you reach that, you actually found the solution. And the reason why I would stop the search is that if you reach the node that has a node ID 200, it means that you are in the goal I was looking for. And when I append the functions, the only thing I do is that I'm adding an edge, of course. And then when I'm adding the edge, I just compute the path, and the amount of error is just a number of frame. So basically, the only thing I'm trying to force the search here to do is to find the shortest animations that will take me from one frame to another frame inside of my animations. So I will probably start at node 0. So if I'm starting at node 0s and I'm trying to reach node 200, and I'm asking to find the path, and it said it found the solutions, and it did it in 26 frames, I can generate the animation out of it, and I can display this animation. And basically, that was the solution we found to go from from node 0, which is the frame 300, and you can say 303, 4, 5, 6, 7, 8, 9, 10, 445. So it did jump back in time, and then it reached the solutions. So, and you could test other. Let's try to reach node 500. It did find a solution in 60 frames. That's a bit bigger. So from node 0 up to that pose, that was the shortest path he could find. So branch and bounds allow you to search through your graph depending of an input, cost functions, a goal, and a cost functions, let's say. Now, again, searching information like this, they said deciding what to ask for, said asking for the shortest frames like this might not be useful, again, depending on what you try to do with it. what they are interesting in their case is trying to make the character walk along a certain path. And to do this, I would actually do what they do also. The first thing is I will generate a path that I want to create. So I would do it with cubic Bezier. I will have videos explaining all the mathematics between all those functions that will arrive soon. But basically that's what I have here is the path I want my character to follow. So I want him to start here, walk along this path and reach that point there. And I will compute all the curve distance and trajectory so I can do this. And what I would do is that the cost functions and the stop will be a bit different. I will execute this because it's not really optimized. It will take time to compute, so let it compute while I'm talking. So what is the stop function now? It's actually saying that if the path my character has taken is as long as the path I wanted him to walk along, you've reached your goal. So that's the stop functions. That's the reason why I wanted to stop. And then when I happen an edge, that's where stuff is really not optimized because it's just for testing purpose more than actually making something running fast. What I do is that every time I add an edge, I build the entire animation from that path, and I use that animations to compute the errors between what my character is walking along. So basically, I take every frame of my animation that has been generated, take the distance that the character is walking, and walk at the same speed along the curve I want him to follow, and I compute the distance between every point, and I sum that error as being the entire amount of error for the entire arc. And so basically that's what I'm doing here, computing the entire errors, total distance covered and all kind of stuff, and I create that new path. Now, even the branch and bound in this case will be extremely slow because there is a lot of solutions to walk along that long curve. So what they did in the paper and what I've done here is to say, I will not try to generate that path in one go, as impossible. I will try to find a suboptimal solution. And to do this, I'm basically doing this. You would say you could look for the best path, but only for, in this case, 34 frames. And you find the best solutions and make sure that the character walk along those along the path for those amount of frames. And then I will go back a little, and I will restart from that point, and I will redo a search of 34 frames from there, and then I will go back a little and then redo a search, and so on and so on. So that's how you get a suboptimal, because you might have not found the best ways of walking along the path, but at least every small steps is computable, and you could try to reach it. You could see that's what it's doing here. It said that at the first time it didn't find a solution. Of course, it has only 12 frames of animations, so it didn't find, and then eventually it did reach the end goal at some point, and then we could see how it did it. So I can generate the animations, and we could display this animation here. And we can see how he managed to walk along. I have absolutely zero constraint on the speed. I'm not asking him to do anything except walking. It is not even has any real intent to say you cannot stop. The only thing that I'm doing is that I'm putting the goal a little in front of him. So the errors keep accumulating if you refuse to walk, let's say. So there is other cost functions that could be more complex. So we could try to force him to make sure that it doesn't go through stops and all that kind of stuff. It was just here as a test to see if we could generate a path through an animations this way. I haven't implemented the entire paper. As you can see, the feet are sliding. I didn't add the foot lock. That I would need to actually put in animation data at the first step to say that's a transition. You need to make sure that your feet are not sliding, all that kind of stuff. I've skipped that part because really what I was interested in was the motion graph. I hope you enjoyed this motion graphs video as much as I love this paper. It's really a paper that starts a lot of different papers at the end. There is a bunch of papers talking about how to improve the graph generations, the amount of transitions they can take. There is papers that use this to say how can we use this as a runtime in video games, that kind of stuff. So there is a lot of papers at the end. And it's really the paper I always come back to as soon as I try to design something. Usually I come back to this one as a ground idea before starting to do anything more complex. So I hope you enjoyed it and see you next time.